So section 14.4, lengths of curves. Well, this is something that we covered in Calc 2, actually in three different versions, in the function version, the parametric version, which is the formula that we have here, and then the polar version of it. Well, so we're going to go back to this arc length, and well, briefly, the way we got to, I'm not going to do the whole derivation. Actually, if you want to see the entire derivation, you can see the video for this section on the 251 lecture modules that I have on Canvas. So you want to see the details. But essentially, we have a curve, and then so essentially this is based on finding the length, which creates a right triangle. That's our delta x and our delta y. That is the increment in the x's, the increment in the y, and well, we can call this the delta L. All right? And of course, the idea was to have this length as tiny as possible, to have a really good refinement, and then add infinitely many of them, right? So, and when we add infinitely many of these partitions as tiny as possible, that's basically a Riemann sum, and that gave rise to the integral that we have here. All right? And well, from here, this delta L is essentially the square root of delta squared x plus delta squared y, which is basically the Pythagorean theorem, and which gives rise to this length. Add infinitely many of those, and you got it. It's the arc length. So this time we're going to extend this concept of arc length to 3 dimensions. So it's just add one more term and make it uglier than it was in calculus. And yes. All right, so let's incorporate the vector notation. Well, back in Calc 2, we just called it a parametric form and then polar form. Well, in this case, we incorporate the vector notation, either the ijk or the component form, either way. And one thing to keep in mind is that this whole expression right here, which is the square root of the sum of the squares of the derivatives, is nothing other than the magnitude of the velocity vector. All right? So, but back then, I didn't tell you about magnitudes of vectors in Calc 2 because we didn't get to see vectors. So instead, we went the Pythagorean way, the distance way. Right now, we're doing this into the magnitude of the derivative. All right? Well, just as part of the notation, this v of t is r prime, is the derivative. Okay. So let's look at one example. Find the length of the curve r of t, square root of 2 times t. Be careful, this t is outside of the radical, it's not inside. In the direction of I, e to the t in the direction of j, and e to the negative t in the direction of k. So number one, let's list our x component, that's root of 2 times t, the y component, which is e to the t, and the z component equals to e to the negative t. That means x prime is root of 2, y prime, it's the derivative of the exponential, which is just itself, and z prime equals to negative e to the negative t. All right, so we have all the information that we need actually I didn't write down the interval t in the interval 0 to 1. All right, I didn't type that part. So S, in this case we're going to call this lowercase s. Back then we called it L. So S equals to the integral from 0 to 1 of the square root of the x component squared plus the y component squared plus the c component, the derivative rather, quantity squared. All right, so let's simplify the radicand. So root of 2 quantity squared, that's just 2, plus e to the 2t, and then plus e to the negative 2t. All right. And here's where the fun begins. How are we going to simplify this? Well, there's a couple of ways, and I'm going to show you the short way. I think for the long way, which is a different approach, it might be I know it's longer, but might be a friendlier approach when it comes to following the logic. I think for that approach, I will create a separate video. So for now, well, typically, and you might have noticed this pattern when back in Calc 2 when we covered this arc lengths and surface areas. Every time we were simplifying that humongous radicand, we always got this perfect square trinomial somehow. So, for example, this quantity, and yes, you're not expected to like know this from the top of your head, but what if you had this e to the t plus e to the negative t quantity squared? All right, so e to the t squared, well, that is e to the t plus e to the negative t times itself. So e to the t times e to the t, that's e to the 2t, e to the t times e to the negative t. Well, doesn't that cancel to 1? And e to the negative t times e to the t, another 1, and e to the negative 2t. Well, combine these two to get a 2. Which is the same expression in the radical, inside of the radical, right? So in this case, sometimes we need to take backwards with perfect square trinomials. For example, in the arc length problem in Calc 2, we had expressions like this, you know, like an x to the 4 plus 9x to the second plus, plus, let me make this work, plus 6. Plus 9. And well, in this case, this is a perfect square trinomial. Thinking backwards, that's x squared plus 3 quantity squared. All right, so we got something like this backward. You might remember something like this from arc length. Well, with exponentials, it's not that straightforward. All right, so well, we're gonna go back to substitute this integral from 0 to 1. That's the square root of e to the t plus e to the negative t quantity squared dt. And what's going to happen here? Don't the radical and the square reduce? And what happens when we cancel the radical with the square root? I mean the radical with the square. They cancel out. However, be careful. For all x, what's the square root of x squared? Plus or minus or absolute value, right? So, but in this case, think of the expression inside of the parentheses. Do we really need these absolute value bars? These exponential functions are never going to be negative, so nor even 0. So no need in this case. In other cases, we will have to have this these absolute values. All right. And well, from 0 to 1. The integral of e to the t is itself e to the t minus that becomes a plus e to the negative t from 0 to 1. And well, the rest of the problem, fundamental theorem of calculus, f of b minus f of a. So that's e to the first plus, wait a minute, that's supposed to be a, no, it's a plus, this is a minus, minus e to the negative 1. That's the upper limit minus lower limit e to the 0 minus e to the negative 0, which is also 0. But well, what is this going to be? 0? And e to the first is simply e minus 1 over e. And that's the arc length. And I mean, very similar to Calc 2, except that we only added 1/3 component. All right. So, let's see, for the next example, which is in 2 dimensions, find the length of the circle r equals arc cosine t. But there's a double t right here. It wasn't supposed to be there. And r sine t. And in this case, well, length of the circle, even though we are not given any limits of integration, so when we want to go around, I mean, one cycle, what are the limits understood to be? So one cycle, it's 0 to 2 pi, right? So 0 to 2 pi, well, so the x component equals r cosine t, that means x prime, equals negative r cosine t. The y component, which is r sine t, that means y prime equals r cosine t.
X prime being negative r sine.
Negative, oh yes, negative r sine, yes, negative r sine. Thank you. And let's see, so let's set up the integral. So that's from 0 to 2 pi. That's the square root of the derivative of the x component squared. Plus the derivative of the y component squared. And careful when simplifying this one, because that power outside of the parentheses is going to affect both the r and the trigonometric function. So that's the integral from 0 to 2 pi. And well, so that's going to be r squared sine squared plus r squared cosine squared t. And well, I think you can see where are we going to get here, because if we factor out the r squared, we're going to get sine squared plus cosine squared. And what's that? So that's going to be 1, right? Which is the integral from 0 to 2 pi of the square root of r squared, which is the integral from 0 to 2 pi. And what does that reduce to?
R.
Absolute value of r. All right? Absolute value of r, because in this case, we never said anything about we never set a condition that r is positive. I know it's a circle, it's a circle, and well, it's a physical object, if we will, so technically there's no negative radii. Well, but in this case, parametric equations, however, can have these negative coefficients in some cases. So, and in this case, given the signs of these parametric equations, each component may map. For example, what if I have the vector valued function negative 4 cosine t and 4 sine t? The position vectors are going to be vectors pointing to the third quadrant, right? So in this case, it's a matter of position. So in this case, that's why we still have that absolute value of r. And the integral of dt is t from 0 to 2 pi, which is 2 pi times big R. All right? And I mean, this is nothing other than the formula for the circumference of a circle, right? The 2 pi r. But in this case, well, we are giving it a character of a parametric equation, and well, if these parametric equations have negatives in their coefficients, well, that's where we get these absolute values too, so we don't get negative circumferences, right? All right, well, the next topic, it's going to be a little bit weird. Okay. So far we have defined all these vector valued functions, x, y, or x, y, z, second, 2 dimensions and 3-dimensional respectively. And those functions are functions of the value t. All right? And also for the sake of simplicity and to make our lives easier, we have related these vector valued functions as position with respect to time. I mean, it makes sense because x, y, z at different points, at different values of t, and well, we did all the mapping, we did an example, different values of t, different values of time. However, so yes, all those functions that we work relate time with position. However, what if a given vector valued function relates something other than position and time? All right. What if, for example, in this case, the parameter t is not time? What if in this case or rather it's still t, but rather the result is not position? It's, I don't know, temperature, for example, or volume, or pressure. Well, depending on, some of you may look at this kind of applications in the engineering field, in parameterizing models to define not position versus time, maybe position versus volume, position versus temperature, etc. So in this case, there is an actual condition that if by looking at the vector valued function, find the magnitude of the velocity. If the value is 1, well, then we are going to have that vector valued function. It's actually defining or parameterizing arc length, not position. I mean, not time, rather. And well, in this case, we're going to describe this. It's very similar. It's very similar, but in this case, we're not going to integrate from between a and b. It's from a to some value of t, and the derivatives of the vector components are going to change a variable u, and that u, again, it's going to be whatever defines the new parameter, which in this case, well, it's going to be for arc length. And again, you can parameterize pretty much every single property: volume, temperature, time, pressure, concentration of a solid for a chemical reaction, you name it, right? But in this case, we're going to focus on arc length. So this new function is going to be the arc length parameter. All right. So this is not going to be pretty. It's going to be a lot of fun, right? Well, I think we have different definitions of fun, right?
Yeah.
Don't worry, we're going to do this together. You're not alone on this one. We all have to go through this. So, okay, find the length function, or yes, the arc length function for this, and it's only a 2D, which is great. Okay, and then rewrite r as a function of s, but that function of s is no longer going to be a vector valued function that relates time and position. It's going to relate position and arc and position and distance. I know it's kind of crazy. Position and arc length, value of arc length. Well, so number one, x component, that's 2 plus t, and the y component equals to 2/3 of t to the 3/2. Well, differentiating these two, it's, well, x prime and y prime, that's a 1 and t to the 1/2. All right? So, well, in this case, this is where it's going to get a little weird, because we're no longer going to use the variable t. We're going to use a new variable. And let me go back to the formula. So, because one of the limits of integration is t to actually denote the arc length with respect to time, well, it would be kind of weird or awkward to back substitute a t over somewhere we already have a t, so that's why we just changed the letter. Okay, so in this case, this is, well, simply 1, and this is going to be u to the 1/2. Okay, so let's set up s of t equals the integral from 0, that's the lower limit, and yes, I know we have a 0 to 3, but in this case, since we want An arc length function, well, from 0 to whatever value, and that's the square root of the sum of the components plus u to the 1/2 quantity squared du. Okay. So this is the integral from 0 to t of how about 1 plus u, and instead of radical to the 1/2 du, and well, we can evaluate this integral by substitution, but no need to show the u sub, the u du, because the derivative is, and actually I don't want to use the u substitution because I'm already using the letter u, so I'm just going to go and integrate this. That's a 1 plus u to the 3/2 over 3/2, which is the same as 2/3. All right, from 0 to t. Okay, let me continue on this side. Upper limit, which is 2/3, 1 plus u to the 3. Oh, wait a minute. So 2/3, 1 plus u. Oh, come on. 1 plus t to the 3/2 minus 1 plus 0 to the 3/2. So 1 plus t, well, it's just 1 plus t. To the 3/2 minus, well, 1 plus 0, which is 1, and 1 to the 3/2 is 1. All right? Okay. So this is our S, which is our arc length parameter. All right? So what's next from here? All right. Well, then we need to rewrite our original function, our original vector valued function, as a function of S. Okay, so this is what I'm going to do. Let me write the S function that we just found. S equals to 2/3, 1 plus t to the 3/2 minus 1. Well, so in this case, I'm going to solve for t, and whatever I get for t, I'm going to go back to the original vector valued function. Bless you. And rewrite this r of t in terms of s. Okay, so first I'm going to multiply both sides by 3/2 to get 1 plus t to the 3/2 minus 1 equals 3/2 of s. Okay, my 5's and my s's look similar, so I'm going to make it look like this. And then I'm going to add 1 to both sides. That's 1 plus t to the 3/2 equals 3/2 of s plus 1. And then, well, to keep solving for t, we have a power of 3/2. We need to raise to the reciprocal of the power, which is to the 2/3. That's 1 plus t equal to 3/2 of s plus 1 to the 2/3. And finally, t equals to 3/2 s plus 1 to the 2/3 minus 1. Okay, so this is the t that we will go back to the original vector valued function, so that that vector valued function, it's no longer going to define position versus time. It's going to be relating arc length versus position. All right. So let's see. So let's go back. Instead of writing r of t, I'm going to write r of s. All right. And okay, let me delimit this. So this will be r of s, because it's no longer going to be a function of t. It will become a function of s. That's okay. Go back to, that's going to be 2 plus t, but in this case, what's t? This t is this humongous mess right here. 2 plus 3/2 s plus 1 to the 2/3 minus 1, that's the x component, comma, the y component, which in this case is 2/3 t to the 3/2. Okay, 2/3 instead of t, I'm going to replace with, again, this humongous mess. So that's going to look like brackets 3/2 s to the 3/2 s plus 1 to the 2/3 minus 1, and the whole thing raised to the 3/2. All right. So that's that's the arc length function. This is no longer a position versus time function. This is an arc length function. All right. So let's just simplify a little bit. Actually, there's not much to simplify other than 2 minus 1, and well, that's something. 3/2 s plus 1 to the 2/3, and well, okay, so that's our arc length function. No longer a position function again, and I'm gonna be making this mentioning this just so. Okay, arc length function. All right. So this is the next part of the question. Well, that's where it's gonna get fun, but that's the whole. What's it's going to summarize the whole thing. Well, what is the magnitude of the derivative of this? Ooh. Let's take the derivative of this. Let's get r prime. Don't worry, you got this. I got you on this one. Okay. The first component, the derivative of 1, which is 0, times, how about a mini chain rule here? 2/3 in the front, times the inside intact, and 2/3 minus 1, isn't it negative 1/3? But by the chain rule, the derivative of 3/2 s plus 1 is 3/2, which nicely reduces, cancel the 2's, cancel the 3's, all right, which is going to be pretty cool. All right. Oh boy, the y component. Well, first of all, let's analyze the function. This is going to be a pretty cool chain rule problem, but let's break it down. Number 1, we have an outermost layer, something to the 3/2, and then an inner layer, and an innermost layer, which is this linear. Okay, remember this? Okay. Let's differentiate the outermost function. Okay, the outermost function. Forget about the mess right here. What is 3/2 multiplied with 2/3? Oh, that's going to reduce pretty nice. 3/2 times 2/3. Leave the inside intact. And minus 1. And what is 3/2 minus 1? Isn't that 1/2? Okay, well, that's differentiating the outermost layer. I'm going to need more space. And maybe here. All right. So now we're going to go with the inner layer. Okay, let's look at the second function. All right. Second function. What's the second function? The inner one. That is this whole thing. That is 2/3 in the front. 3/2 s plus 1. When 2/3 minus 1, isn't that a negative 1/3? And that the derivative of -1, that should be 0, right? And then we have an innermost layer. Okay, the next one. All right. What's the next layer? The derivative of 3/2 s plus 1, which is just 3/2. Okay, this is going to reduce anyway. Cancel the 3's, cancel the 2's, and let me close the bracket. And well, this is going to reduce number 1 to simply, well, not that simply, 3/2 s plus 1 to the -1/3, comma, also, let's cancel these coefficients as well. And that's, okay, let me write this factor in the front, the 3/2 s plus 1 to the -1/3, bracket 3/2 s plus 1 to the 2/3 minus 1, the whole thing to the 1/2. Okay, that's only the derivative of the vector valued function. Oh, let me close. All right. Then want us to find the magnitude of this. That is the square root of this quantity squared plus this quantity squared. Okay? Let's go ahead and do this. So the magnitude of the derivative of the velocity vector, well, wait, no, that's not velocity vector, this is arc length. Let me take it back. This will be the square root of the first quantity squared, that is 3/2 s plus 1 to the -1/3, that whole quantity squared, all right, plus curly, let me use curly braces, 3/2 s plus 1 and 3/2 s plus 1 to the 2/3 minus 1 quantity to the 1/2, the whole thing squared. It's going to reduce really nicely. You'll see. In the end, you will say it was worth it. Okay, number 1. Oh, -1/2. Oh wait, no, that's not a 1/2. That's a 1/3, right? It was supposed to be a 1/3. -1/3 rather. Okay, so this will be the square root of 3/2 s plus 1 to the -2/3 plus, okay, be careful here, because number 1, and let me highlight here, we have one factor here, and we also have a second factor here. Okay? So this power of 2 will affect both the exponent -1/3 and the exponent 1/2. You guys following me here? All right. So that's 3/2 s plus 1 to the -1/3 times, cancel the 1/2 with the 2. That's going to be simply 3/2 s plus 1 to the 2/3 minus 1. All right. And we're almost there. We're almost there, believe it or not, despite this looks, despite we're going bananas with this, we're getting there. So, okay. One thing worth notice, oh, this is supposed to be a 2/3. All right, 2/3, because 2 multiplied with the -1/3, that becomes a -2/3, right? It's these two. Okay. One thing to notice here is the GCF. These two are greatest common factor, right? Okay, so And this quantity right here, it's essentially being multiplied by 1, the first term. Okay, I'm just writing that phantom 1 in there. I mean, it's there in spirit. I'm invoking it. I'm summoning his spirit, right? Because we need him. Okay, so I'm going to factor out this factor in that I box in red. And that's 3/2 s plus 1 to the negative 2/3 times 1 plus the quantity in brackets. All under the radical. Okay, and well, these ones cancel. 3/2 s plus 1 to the negative 2/3 times 3/2 s plus 1. No, this one is supposed to be here. Okay, we have the same base. What do we do with the exponents? The same base, 3/2 s plus 1, 3/2 s plus 1. What do we do with them? What is negative 2/3 plus 2/3? So 3/2 s plus 1 to the 0 power, which is the square root of 1, which is 1.
Oh my gosh.
Okay, so all this mess that we need in the second part, this is okay. All this mess is only the verification that the new function we obtain, it's indeed an arc length function. All right, it's like when you make a test, for maximum and minimum. So you pick a test value. Okay, if you plug in a test for increasing, decreasing. If you plug in a value and you obtain negative, what does that mean? Decreasing, right? If we plug in a derivative, if we plug in a derivative and a number on a derivative, we get increasing. We get positive. Oh, come on, I gave you the answer. It means increasing, right? Happens to me all the time. I don't know why. So in this case, well, the test is that we take the derivative of the arc length function, find its magnitude, and our final answer has to be 1 in order to conclude, oh yes, this function is an arc length function. And that's the theorem that we have over here. Whenever we have an R of S function, if the magnitude of its derivative, that means that our original vector valued function describes arc length. All right, for example, and this is what I was mentioning at the beginning of this topic. Maybe there is another condition that if you get maybe 0, for example, maybe this function is a parameter of temperature, maybe something else. But in particular, this is if the magnitude of the derivative of the given vector valued function equals to 1, well, what do we have? It means this is arc length. And well, let's now use this theorem and verify for these two functions. Well, so all we have to do is find the derivative. So x equals to 2 sine t over 2, and y equals to cosine t over 2. That means x prime is, what's the derivative of sine? Isn't that a cosine? 2 times cosine t over 2, and by the chain rule, that's a 1/2, which reduces to cosine of t over 2. In the same way, the derivative of y prime, that's negative 2 sine of t over 2 times 1/2 by the chain rule, and that half times the 2, that's negative sine t over 2. So now we need to make the test. to determine if that given parametric this given vector valued function, which initially we just related it conveniently as position over time. That's what we have done so far. Now we're going to determine if this function indeed is also an arc length function. So take the magnitude of the derivative, and that is cosine t over 2 squared plus sine t over 2 squared. All right. And well, this is going to be cosine squared t over 2 plus sine squared t over 2. And what is that quantity inside of the parentheses? It's one of the identities. Cosine squared plus sine squared of whatever angle equals 1. Alright, so that's the square root of 1, which equals to 1. What is our conclusion? Is this an arc length function?
Yes.
Yes. Or like in infinite sequences and series, well, you obtain this result in your limit, converges or diverges. Well, depending on the test, well, it's either one or the other. Well, in this case, we're testing a vector valued function to be an arc length function. And I know the process was a little painful, but that's actually to prepare you for the next section. All right, so you don't want to miss, huh? Yeah, this is basically the warm-up. Yeah, that's a good call. That's basically the warm-up. All right, let's look at the second example and determine whether this vector valued function is parameterizing arc length. All right, so x equals cosine t, y equals sine t, and well, apparently looks like, but there's something here. So x prime equals a negative cosine y prime. Again, I know. Negative sign. Cosine t, and z prime equals to 1. Now let's make the test. Let's make the process. The magnitude of the derivative of r. That's the square root of negative sine squared, negative sine t squared plus cosine t squared plus 1 squared. Well, sine squared plus cosine squared, isn't that 1 plus 1 squared, which is 1? Well, in this case, this is the root of 2. So converges or dive? Oh wait, no. This is arc length or not arc length? Back some nightmares from infinite series. No, this is not an arc length function. So yes, we can safely say that this function describes position versus time. Now going back to the previous example, because in this case, this was indeed an arc length function. We can rewrite it as an R of S. All right, not in the second function. All right. Okay, the last problem in the example 5. Represent example 4b so that the parameter is arc length. That is, we're going to do something like in the previous example, in which we get the arc length, solve for S, and go back, substitute for, basically all this process right here, solving the equation for t to redefine it as a function of S. But the good thing is we already have a lot of the work from part B. All right, and in this case, well, so let's see. Yeah, we're gonna do this in 4 minutes. That's fine. So that's S of t equals the integral from a to t of this, actually it's the magnitude of the derivative of r of t with respect, in this case, u, actually not r of t, it's the u. Recall that we changed the new variable, and then we get back to t. Well, so this will be the integral from 0 to t. Well, in this case, I didn't mention, or I didn't specify what's the interval. So let's just say t is greater than or equal to 0 for the sake of simplicity. So from 0 to t, well, do we really need to find this again?
No.
We already got it. It's root of 2, right? Mm-hmm. Root of 2 dt. And what's the integral of the square root of 2? Square root of 2t. And evaluate it from 0 to, hold on, u. du, not dt. That's u from 0 to t. And, well, this is going to be the square root of 2 times t. This means, okay, let me put this together. S equals to the square root of 2 times t. All right. And t equals s over the square root of 2. So we may now go back. So now we're finding the transformation that once we substitute in the original vector valued function, this will indeed be an arc-length function, which is the same way we did, the same thing we did over here when we solved this humongous equation for t. Then what did we do? Plug this back in the original vector valued function where it corresponds for t. But, well, this last example, it's a lot simpler. It's not that humongous. So, well, originally our r of t, which is cosine t, comma sine t, comma t. Well, we made the test, and it turned out being that this was not an arc-length function. Now, making the substitution r of s, that's cosine of, instead of t, that's well, let me highlight just so you can see what am I doing. Over here, and over here. That's cosine of s over root of 2, comma, sine s over root of 2, comma, s over root of 2. So this function has to describe arc length. And, well, of course, let's make the test. Let's find the derivative. I know it's not gonna take too long. So r prime, I'm doing this just so we can verify our results. So that's gonna be negative 1 over root of 2 sine of s root of 2 over root of 2, 1 over root of 2 cosine s over root of 2, and the derivative is simply 1 over root of 2. Okay, so the magnitude of this derivative, that's well, the square of negative 1 over root of 2 sine of s over root of 2 squared plus 1 over root of 2 cosine s root of 2 squared plus 1 over root of 2 squared. Whoops, let me make this look nicer. And, well, so that's okay. The square root of 2 quantity squared, that's simply 1/2 sine squared s over root of 2 plus 1/2 cosine squared s over root of 2 plus 1 over root of 2 quantity squared, isn't that a 1/2? And, well, just to conclude, common factor is a 1/2. 1/2 times sine squared. Let me just write sine squared plus cosine squared plus 1/2 sine squared plus cosine squared. Isn't that just 1? And what are we going to be left with in the inside of the radical? The square root of 1/2 plus 1/2, which is the square root of 1, and as expected. All right.